Hello, good morning, good evening, good afternoon, everybody, wherever you might be. It is my great pleasure to welcome my former student, MARIUSZ Tobolski, who will speak about his joint work with my current student, Atul Gove, and John Quick from the Arizona State University. Okay, MARIUSZ, it's all yours. Take it away and glue topological graph sister algebras. It's all yours.
Thank you. Thanks, Piotr. And it's always a pleasure to give a talk at the seminar. I think it's been a while, but I'm happy to give a talk again here. And this is, as you said, a joint project with Atul and John. And it started when both me and Atul, we were visiting ASU. And the first day we met, I asked Atul what you are working on right now. And he told me, well, I'm working on this pullback theorem on topological graphs. And I said, well, that's funny because I'm working on the same problem. So maybe we can do it together. And that's how it all started. And I'll give you some motivations on what we want to do. But the first kind of like a motivation is that we already with Piotr and there are many other papers on this subject, we are doing this kind of gluing for graph sister algebras. So now we're upgrading it to topological graph sister algebras. And the motivating example will be given by this quantum balls, odd dimensional quantum balls. So that's the overview of the talk. I'll first give you the definition of topological graphs and topological graph sister algebras. And after that, I'll give you this example from noncommutative topology because this is noncommutative geometry seminar. And from that, I'll start gluing those algebras and graphs. And I will end at the theorem that generalizes the theorem known in the literature in this context. However, a disclaimer is that this is work in progress. So there are some questions that are still open and some conditions that we want to get rid of. Some conditions maybe we have too many of them, but you'll see during the talk. Let me start with topological graphs. So a topological graph is really a generalization of a graph where you put topological spaces for edge space and for vertex space. All right. So first E1 and E0 locally compact Hausdorff spaces. We think of E0 as a vertex space, so as vertices, and E1 as edges. We have a range map, which is like the end of each arrow. And we assume that this map is a local homeomorphism. And this is a very important assumption for this theory. Right? So this is the assumption that Katsura came up with. It's very similar to étale groupoids. So if you ever work with étale groupoids, you also have this assumption of a local homeomorphism. The thing is, we want preimages of every point to be discrete, right? So we want the preimage, the fact that for local homeomorphism, preimage of every point is discrete, and we will need this. We'll be summing over those sets. So we don't want to think about integrals or infinite sums, we don't want to think about integrals. That would be topological quivers. And then we have the source map, which is only assumed to be continuous. So we have just two locally compact Hausdorff spaces and two maps between them. One is a local homeomorphism, the other one is continuous. Let me give some classes of examples. So, of course, discrete graphs will satisfy this because there we have discrete spaces with discrete topology, and it's all locally compact Hausdorff, and every map is a local homeomorphism between discrete spaces, and continuity is also for free. So this is a very kind of a trivial class of examples from topological point of view, but of course, it's all very complex if you just look at graphs, any graph sister algebras. Another class of examples is coming from homeomorphisms on locally compact Hausdorff spaces. So let X be a locally compact Hausdorff space and let phi be a homeomorphism on that space. Then both your edge and vertex space, you take X. For the range, you take identity. And for the source, you take this phi. Okay. And then you can see that, of course, identity is a local homeomorphism. phi is continuous, you could even, well, choose one or the other for the phi or the identity. And then another class of examples. This is something we are working on in a different project with also people from ASU, with Ben Jones, Matthew Gillespie, and Lucas Hall from Michigan. Question on the chat.
No. It's a conversation with me.
Sorry. So, and here, I think it's a nice class of examples, even for discrete graphs. Just take the discrete group or finite group even. You get some nice examples of graphs. So you take G to be locally compact Hausdorff group. Of course, I just forgot to write down Hausdorff, but it's implied whenever I talk about locally compact spaces. And gamma is a discrete subgroup. Then this map, the orbit map, will be a local homeomorphism in that case, because gamma will act on G properly discontinuously. So you might not get a covering map if G is not like path connected, locally path connected, but you'll always get this local homeomorphism. And for phi, you take an endomorphism because I mean you want to use the group structure to get a nice example.
May I have a question?
Yeah, sure.
So in your examples number 2 and 3, you are talking in fact about action groupoids. And then you have an additional operation of composing arrows. Does it play a role in these examples or not at all?
So it's a good question. So first, if you could specify, so an action groupoid is when you have an action, you're talking about just action of a group and you make a groupoid out of this, right?
Yes.
Okay, so short answer is I don't know.
Yeah, I don't see a group here.
I mean, we have, in the second example, it's integers, right?
Integers.
In the second example is the integers, and in the third example is this discrete subgroup that acts on G. So it's both.
Okay.
Both examples are of this type, because we're interested in this class 3 because you can think of some like free actions now, principal actions. I mean, those will be exactly free and proper action because this is a subgroup of a locally compact Hausdorff group. Okay, but so these are some classes of examples so that you can see that with topological graphs, you can go well beyond discrete graphs and have really interesting examples. And it will get more and more kind of like sophisticated and different from discrete graphs during the talk. So if you're familiar with graph sister algebras and discrete graphs, I'll be trying to point what are the main differences here. So that's the definition of a topological graph. And now I want to talk about some special sets of vertices, special subsets of the vertex space that is really important also for directed graphs. And then there's an analog of all that. So we'll have sinks, infinimeters, and more. So I'll start with defining what are sinks. So here, sinks, it's not that you're outside of the image of the source map. You have to close it. This is especially important if we'll be looking at, so all those definitions, of course, they have to they have to generalize the thing we know from discrete graphs. However, what is the most important thing are the regular vertices that we cannot change. They have to be this because the regular vertices, they define this ideal of Katsura that defines you the right C-star algebra to begin with. So things are defined like this. So we take the closure. Then the finite vertices, the change here is that instead of having finite emitters, you have just compactness assumption, that there exists some neighborhood of V such that this preimage, so you can take a compact neighborhood if you want. I just wrote like a generalized neighborhood here. So there's some V that contains an open neighborhood of V, and this V could be taken to be compact. And these are the finite emitters, right? So And topology will play a role. You'll see that singular vertices will be more than just infinite emitters and sinks. Infinite emitters, right? So and everything that is not finite is infinite. That makes sense. And then regular vertices, again, you take the closure. So you take finite emitters without the closure of sinks. Yeah.
Mariusz, a stupid question. Is it obvious that E0 finite is
E0
closed?
finite is not closed.
It's not closed.
I think, or maybe I'm saying something wrong here.
So you
I think
don't care
technically
here
to
about
answer the
getting
question,
rid-
it's not
You
obvious.
have that's infinite thing. Okay, I see. Yes. Okay.
Yes, thank you.
Okay,
Yeah, it's
okay,
not
okay.
obvious. This answers the question. Yeah,
So that's why
yeah,
it's hard
exactly,
to know.
exactly.
But still, my question is valid. So what do we know about E0 finite? Is it open, closed, whatever?
So let me think here. I think that E0 finite is an open subset, and I'm not
That's
saying
what
that
it
this-
looks to me, yes.
Yeah.
Okay.
But this is not immediate, as you said.
Yeah.
The same with regular vertices. You also get an open subset, but it's not immediate from this definition. Okay. So regular vertices are everything that is finite without the closure of sinks. Right. So now singular is everything that is not regular. Right. So you're getting and this set, if what I said is correct about finite ones, then this set is closed, right? Singular is closed. This is easy to see. If E0 was open, then this is closed. And so okay, so I sorry for this hiccup, but it's correct. It is an open set, and now singular vertices are closed, regular vertices are open.
Mm-hmm.
And now you can see the first difference is that for singular vertices, you have sinks, infinite emitters, and also the closure of something in the boundary of sinks. So there's more. And this is the kind of like the most annoying thing about working with topological graphs, that whatever you want to prove that you already know for graphs regarding regularity, you have to take into account this closure of sinks. And sometimes it's very difficult to overcome some of the difficulties that they produce. Examples, and now it's really not classes of examples, but actual examples. So take E1 to be just numbers from 0 to 1, open in just open interval from 0 to infinity. I mean the open half. How do you say?
Two-sided open.
Two-sided open, but I wanted to say something. But anyway,
Yeah, we know what you mean.
We know what I mean, and E0 is the real line, and then both R and S are the inclusions. Okay, and we want to look at all those subsets: sinks, infinite emitters, finite emitters, and so on. So sinks, right? We have everything from minus infinity to 0 without 0, right? Because we're taking the closure. So here we're taking the closure. Then the finite emitters will be R without 0. Right? Because there's no chance of getting any compact neighborhood here of 0. If you take the pre-image you take any neighborhood, let's say compact neighborhood here, it will be not compact in E1 because you always have to have this open 0, 1 interval, this open interval here at 0. So finite emitters, everything but 0, regular, and then now it's maybe finite first, or no, should be easy here. So regular vertices are from 0 to infinity, and infinite emitter is just this one vertex 0. And now what is interesting here is that something can be an infinite emitter and also in the boundary of sinks, right?
But every edge is a loop here, right?
Every
Mariusz?
edge is a loop. Yes.
Mariusz,
Yes.
can you hear me?
Yes, I can hear you. Every edge is a loop. That's correct. Yep. So of course it's much more difficult to now visualize those graphs. But you should visualize this like every edge is a loop, and then you have at 0 you have like something happens and you have an infinite emitter. So, and this is also in the boundary of sinks. So this is something that, of course, cannot happen in discrete graphs. And also here, if you forget about the closure, E0 sinks and infinity meter, this is an empty set, the intersection without the closure. So the only the boundary can intersect infinity meters such that you get a non-empty set. So this is one example when you can see that there is something new going on, some new phenomenon. And then another one is also really nice and kind of tricky. Now we take E1 and E0 to be the real line, and the range is just identity, and the source is the absolute value. So of course the range here it's easy to see that also I didn't say anything about this, but it's easy to see that those maps were local homeomorphisms. Here R is identity, so it's a local homeomorphism, and S is continuous, right? Absolute value is continuous. And now from 0 to 1 to infinity, you get like loops. At 0, something happens, and before 0, you get sinks, right? So sinks are from minus infinity to 0. Then there are no infinity meters. Everything is finite here. Regular vertices are from 0 to infinity. So but still we get that singular vertices is from infinity to 0 with 0 included. So you have a vertex that is not a sink, not an infinity meter, still it's singular. Okay, so it's very different from discrete graphs. And here, this is also an example of a topological graph that is, even though all edges are like finite meters, let's say, this will not be a row finite graph. You have to change the definition of row finite. This is what Katsura did. And please try to remember this example. I'll be using it twice, I think, in my talk, because it's a very nice example of something that your intuition from discrete graphs that row finite should be this, that that all edges are finite meters. However, this doesn't work. And the reason is that you have to change this for row finite graphs. When you classify ideals of C-star algebra, graph C-star algebras, then you have this easier classification just by hereditary and saturated subsets, right? You don't have to talk about breaking vertices. And you want to have this property for topological graphs. So if you want to just have those hereditary and saturated subsets to classify all your gradient invariant ideals, you have to think of a different definition of row finite, because this will not do, because exactly this example is where you have some two distinct you cannot classify just by hereditary and saturated subsets. You have to add those some sort of kind of breaking vertices. However, you don't have infinite meters here, so it's really all your intuition from directed graphs is not really useful here. Okay, but let me go.
Mariusz, let me ask you a stupid question. I'm looking again into the definition of this E0 finite.
Yes.
When you say that the preimage of an open set is compact, do you really mean it as it says, or do you mean that there is a compact closure?
Yeah, so I mean neighborhood in a generalized sense. Because it's easier to write down this in just one line, right? If I write open neighborhood whose closure is something, then I'll not. So I mean a generalized neighborhood. By generalized neighborhood, I mean that V can be compact, and it's a neighborhood, so it has some open neighborhood of V. It contains an open neighborhood of V.
Sorry, I think that it is often called relatively compact.
Okay.
Compact after closure.
Yeah. Okay.
Okay, thank you.
Yeah, that's a good question. Someone is always asking me this question, and I'm following Katsura's notation. So you have to blame him, not me. Okay. Now we go to C-star algebras. So I'll define as how do you build the C-star algebra, and you build it by defining a certain C-star correspondence, and then your topological graph C-star algebra will be a conspiratory algebra of this correspondence. So first, your For the correspondence, you always need two parts. First is the algebra, the sister algebra you're working with, and then some right Hilbert module over this algebra. And then you add this additional left action to make it a correspondence. So first we have our sister algebra. This is an easy choice. We take on the vertices, we look at functions vanishing at infinity. And now this is how we build the Hilbert module. First, we take compactly supported functions on the edge space. We define an inner product and norm. And here you see why I need this local homeomorphism property, right? So I really can take a sum here because this is a discrete set over which I can sum. Right? And I'm defining this inner product in this way. And because those functions are compactly generated, compactly supported, sorry, this is a finite sum even, right? So, and this is the norm. And now I'm closing.
Mariusz, can you remind me? You did assume that E1 and E0 are locally
Yes.
compact Hausdorff, right?
Mm-hmm. Yes, I did. So the spaces are locally compact Hausdorff, so I can take functions vanishing at infinity, and I'm looking at sup norms here, right? So I'm closing this the space of compactly supported functions with respect to this norm, and this part after this is actually some sort of a proposition or a theorem proved by Katsura, that this is actually, because it's not immediate and obvious, this is actually some subspace of bounded functions. So these are again functions, right? So you can prove that XE is actually just those bounded functions such that this inner product is a C0 function on vertex space. Okay, and this sometimes it's very helpful. If you know about topological quivers, you know that you cannot do this for topological quivers, where instead of a sum, you have an integral. But here, you can think of elements of XE as functions, which is nice. And then we define left and right action on XE by A. And on the right, we're acting using the range map. And on the left, we're acting using the source map. And now, you can prove that XEAE is a sister correspondence, so you have to check several conditions that this is actually an A-valued inner product and so on and so forth. So this, of course, helps. So this tells you that this inner product is has values in AE and so on. So I don't want to get into the definitions of sister correspondence and Hilbert modules. So I'm assuming that you know that. If there are any questions about it, please don't hesitate to ask. But I have enough material to cover with my talk that I won't be going into details on sister correspondences and Pimsner algebras. Because now, if you have this correspondence, your topological-graph sister algebra is the Pimsner algebra of this correspondence. So what you're doing, so there are at least two ways of constructing this algebra. One is in a very, you just say that it's an algebra satisfying a universal property with respect to some kind of representations of sister correspondences. So a representation would be on a sister algebra, let's say, would be two maps, one from X and one from A. And the map from A would be a star homomorphism, the map from X would be linear. And then you have to satisfy some compatibility conditions with respect to the inner product. And you call this a representation of your correspondence on the sister algebra. And then you choose a sufficiently nice representation called covariant representations. And now Pimsner algebra should be universal with respect to those covariant representations, right? And let me give you examples. So in the case of discrete graphs, this is really just your sister algebra, graph sister algebra. And so your first step of building this representation, this is like the first condition of Kunz-Krieger, and then saying that the representation has to be covariant, this is the second Kunz-Krieger condition. There's also another way of defining this algebra, very concrete, by generalized Fock space representations. So you can also do this, and And you can do this for graphs as well, for discrete graphs too. You have the same construction that is really analogous. Now, for the homeomorphism example, what you get is a cross product. Okay, so you have two classes, graph-sister algebras and cross products by Z. So, and that was the first idea of Katsura, and the paper was entitled "A Class of Sister Algebras Generalizing Both Graph-Sister Algebras and Homeomorphism Sister Algebras." So those two classes of examples. So that was the main idea of Katsura, to get, because we know that they are conspimsner algebras, but he wanted to have something similar to a graph that will be more tangible. And those two classes are examples of algebras of topological graphs. So, for example, you can get the irrational rotation algebra here as topological graph, and we know it's not a graph sister algebra. So this was something that's nice. Now,
but I think, MARIUSZ, if I remember correctly, I think that you can make it into a twisted higher rank graph sister algebra.
Yes, I'm aware of that. I don't know how you do it, but I've been to a talk when someone was explaining that. Yeah, so that's true. So you can make it a twisted higher rank graph sister algebra.
You know, but exactly, but it's not so mysterious. If you want to have just the classical torus sister algebra as a graph sister algebra, you have to have a rank 2 graph sister algebra, and then when these two unitary generators have different colors, and then you obey the definition of a higher rank graph sister algebra, and lo and behold, that's exactly the 2 torus sister algebra, and then it's not such a big deal to have twisting the usual way, Riefel's way twisting when you have partial isometries.
Yeah. That's true. That's true. Yeah. Thanks for that comment. Yeah. Here, this.
May I have a question?
Yep. Sure.
Exactly about this point. So what Piotr was talking about is that you can replace z integers by power of z. Okay. Is it important that this group is abelian? What if you have some finite group acting on X?
So for finite groups, cyclic groups at least, it should work, because then you just say that phi is a homeomorphism. They are abelian, yeah. But for I don't know, I was thinking about this exact question. What we can do instead is to look at this, skew product construction, derived graph construction, and then take any compact group, and then you can recover at least something that is Morita equivalent to this cross product. But I don't know in general, because here we have like very limited possibilities. We can take this S and we can just apply it several times, right? Infinitely many times, and that's your Z. I don't know how to generate from this setting, how to generate other groups, except for this case of this derived graph or skew product, which would correspond to like a trivial bundle, right? You can have actions on topological graphs, and there are papers on that by John Quigg and Valentin Diaconu and Alex Kunjian, where they study principal actions of groups on topological graphs, and also prove a result that if you take this derived graph, the skew product graph, it's more equivalent to the cross product. But from just looking at this, I don't know how to put some other non-abelian groups acting on X. I don't know how to do this.
Sorry, what I had in mind were permutation groups and their actions on some finite even configurations. Even in discrete case, this action of permutation groups on graphs are interesting.
Yes, exactly. That's true. That's true. And you can have also action of any group on a topological graph and look at this. So that's definitely, but from this setting, if you take E1 and E0 to be X, I don't know how to generate a different group than Z or cyclic groups.
Okay.
Okay, so let me continue. So there's a gauge action also, and then here should be C star of E. I was trying to, this is old notation. So this should be C star of E. So there's a gauge action given by those maps. And here tau 0 and tau 1 are those universal representations. So what is this universality of conspecific algebras? Is this that in a sense they are C star algebras generated by by A and X. Right, so you look at elements of A and you look at elements of X. So this tau 1 goes from XE to your algebra, and tau 0 goes from F to your algebra. And you define the gauge action on on vertices, does nothing, and on edges it's just rephasing. So it's exactly the same as for discrete graphs. And then you can prove that because this is a homomorphism, and even for every Z, this is a isomorphism and automorphism. So you can prove that this is actually giving you an action on the whole C star algebra. Sorry for this. This is the one place I forgot to change the notation. So there's a C star of E, and this tau 0 will become T0 in next slides. So sorry for that.
Also, but the idea is this. Sorry. If you're replacing OE with C star of E, are you assuming T0 to be injective, T0 and T1 to be injective?
So you can always prove that the T0 is injective, right? So so I'm taking this universal, and you can prove that this universal one is in fact injective by this Hawk space representation construction, and then using the gauge invariance uniqueness theorem. So let me mention here that for topological graphs with this gauge action, there's also a gauge invariance uniqueness theorem. So what you're assuming there is when you restrict to, because this algebra AE will always be as a subalgebra, not subalgebra, it will, you will have a map, and non-degenerate map from AE to multipliers of your C star algebra. And so in a way, you can think of those elements as being, so that was your question, Atul, sorry. So we're thinking of elements of the algebra of the AE as elements here, and when you restrict your star homomorphism from your algebra to some other algebra, and you restrict it to vertices, it has to be injective. That's the analog of being non-zero on vertices in the graph C star algebra level. So now you're saying that if you restrict it, then it has to be injective. If you restrict it to those elements, tau 0 of F. So you have a gauge uniqueness invariance theorem, and I'll be using this theorem soon, but let me maybe pick up some speed. Okay, so now.
And who proved this gauge invariance theorem?
That was already in Katsura's first paper. So maybe it was known in some other, because of course Katsura's work is based on Pimsner work on Kunst-Pimsner algebras, right? And he refined it, and he found because the Kunst-Pimsner algebras of Pimsner could only give you Kunst-Krüger algebras, so graph C star algebras with no sinks and no sources. So yeah, Katsura's improvement was to add sources and sinks. So now you have also graph C star algebras. So he had to invent this ideal, this Katsura ideal, and because the ideal that Pimsner was using was not sufficient.
Was not ideal.
It wasn't ideal. Yeah. Okay. So that was proved by Katsura, and now let me go to the first main part of my talk. I want to show you, and I think it wasn't done before, that C star algebras of odd dimensional quantum balls are topological graph C star algebras. It is one can prove that they are not graph C star algebras looking at primitive ideal spaces, because there's a classification of primitive ideal spaces of graph C star algebras. And people, when I asked Wojciech Szymański about this, he told me, well, they are Kunst-Pimsner algebras, But I couldn't find any source of in the literature, but I guess it was well known to experts that odd-dimensional quantum balls are consequential algebras. But so the added value of our work will be that now you can kind of see them, right? Because this is all about sister algebras that one can see. So now we will give some topological graphs for those sister algebras, so we can have some sort of intuition coming from topology about this. Okay, and to do all of this, I'll be defining a quantum double suspension. And it's supposed to be an analog of double suspension in topology, because in topology, if you take a double suspension of a sphere, you get a sphere that is 2 dimensions higher, right? So you have 2 dimensions more. And the same for balls. So that was the idea of
let me ask you, Mariusz. Yeah. So that's as defined by Szymański, right?
Yeah, exactly. Quantum double suspension is defined by Hong and Szymański. It was first defined, I think, in the paper on quantum spheres already. And then they were using it to define quantum balls in the paper on quantum balls and mirror quantum spheres.
So that's perfect. And I understand that this is some glorified tensoring with compact operators using Busby invariants.
Exactly. But now, so I'm very happy you said all of that, because I will not say it. Because the original definition is, let's say, it talks about essential extension, Busby invariant, and it's very difficult, but one can prove a very, like a proposition that will give you like a very concrete version of what this algebra is as a sister subalgebra generated by some elements. So let me start with recalling the graph presentation of the Teplitz algebra. If you want to talk about compact operators, we want to talk about the unilateral shift. So we're talking about the Teplitz algebra. And I'm just reminding you that this is the graph of the Teplitz algebra, and this notation I'm going to use in my definition. So the partial isometries with edges, and we have 2 projections corresponding to vertices. So now the definition proposition, which is proved by Hong and Szymański, is that the quantum double suspension of a unital sister algebra is the sister algebra of A tensor T. And here, because Teplitz algebra is nuclear, I'm not worrying about what tensor product I'm taking. And this sister algebra is generated by elements A tensor PW, for any A. And then I have those 3 additional elements, 1 tensor PV, 1 tensor SE, and 1 tensor SF. So the whole idea is to somehow put A here, right? I'm going to put A here, and this will be this additional piece that is independent of A. It's all one. Now,
Mariusz, a stupid question. So which elements of the full tensor product are not in this subalgebra?
That's a very good question, but I think that what would be the answer? Let me think.
Oh, wait, this is generated by APW. Okay.
Yes, yes.
So I don't understand these things written after the comma. So are these the generator or not?
These are the generators generated by this and this and this and this. Yeah, these are 3 additional generators I'm adding.
Ah, okay. So I understand. Yeah. So you can multiply by A only PW. You cannot multiply by AP. Okay, I've got it. Okay, sorry.
Yeah. So there, you're right. Actually, there are many things that are not in the sister algebra, right? A times PV will not be there, right?
I somehow misread it. I understood that these are generators, and I was multiplying it by A, but of course.
Yeah, sure. Mm-hmm. Yeah, thanks.
Okay, I see it now. Thanks.
So this is a good working definition. If you want to prove something about this algebra, this is the definition to look at. And this is something I already said. It's supposed to be an analog of the double suspension topology. And this whole discussion about Busby invariant is that somehow the functions vanishing at infinity on the plane are substituted by compact operators, right? You should think about this quantization like this. And now, if A is a topological-graph sister algebra, you can have an action, and you can see that here I'm preparing for the use of gauge invariance uniqueness theorem so I want to have an action on this algebra. If A is a topological graph C-star algebra, then you can take the tensor product of actions, so the gauge action on A and the gauge action on the tablets algebra, and then you restrict it to the subalgebra to get a natural action of the circle.
Sorry.
The diagonal action, right?
Yes, the diagonal one. Yep.
Oh, yeah, yes. Okay.
So now, this was already done for graphs. That for graphs, Hong and Szymański, they prove also that if you take this quantum double suspension of a graph C-star algebra, it's again a graph C-star algebra of a graph called the double suspension of a given graph. However, as you saw, I was using unital here. That's why my vertex space, I wanted to be compact. And then you can prove this is very similar to like for graphs, when your vertex space is finite, your algebra is unital. Here, your vertex space is compact, the algebra is unital. And this is if and only if. So now we're assuming that we have a compact vertex space, and this is how you define double suspension graph. You're adding, and here now I'm sorry, I don't have a nice picture. I forgot to prepare it, and only now I thought that it would be nice to have a picture. But so just on symbols, you're adding a new vertex to your vertex space, and this should correspond to this picture of the tablets algebra, this new vertex. So the suspension of a just one point graph would be the tablets algebra. So you're adding a new vertex with just one vertex, and you add a loop. And from this vertex, you have to have edges going to everything you had in your graph. That's the idea, right? That's why I was saying that you have, like for quantum spheres, right? So if you start with one graph, like the one loop, then you have another loop and edge there. And if you start with two loops, then you're adding this third loops, but you have to go to every vertex, right? So that's the idea here. So let me go back to those symbols. So you're adding one vertex and one edge, and this edge has to be a loop, and it's given here, right? That both source and the range of this is W. And then I'm adding new edges corresponding to vertices here. And for those edges, the source is W. So you start in W, and then you go to the vertex, you kind of, because you're using the same set E0, right? So you're adding a lot of edges that start in W and end in every edge of the graph you started with. And then you also have your edges that you had in your graph previously. And those, they start and end when they started and ended.
Mariusz, a sanity check, if I may. If I start from a zero-dimensional sphere and I keep applying quantum double suspensions, I will get all even-dimensional quantum spheres.
Exactly.
And if I start from the circle, I'll get all Waxman-Soibelman quantum spheres, right?
Yes. So that's the idea, and that's why they defined it this way, because they noticed this pattern, and it's very nice to have this now for topological graphs. And we're generalizing what Hong and Szymański did in the context of directed graphs. And then we also have this, and this is important for the proof that I'll give you. I decided to give you at least one proof with some mathematical reasoning, not just definitions. So if you look at this space, it's very easy to see that this is 1 point and E0. So this will decompose as just one-dimensional space, and I'm adding this vector delta W, like this characteristic function of W and E0. And here we also have this decomposition of the Hilbert module, because the Hilbert module structure and the inner product is defined by range. And we see that an edge here ends in W, and then edges here in this X E0, which are edges, you look at functions restricted to this E0, right? Of course, it's a little bit confusing to use E0 here and here as the same set, but I hope it's not too confusing. So if you restrict it, then you have edges that all end in E0, and now they all start in W, right? So we have three classes of edges. We have this one edge X, and this is this piece. We have all those edges that end in E0, but they start in W, and then we have those. And that's this decomposition you're getting. And it will be important for, like, if I want to write a formula now for a representation of this correspondence on a C-star algebra. Okay, so let me go to you'll see it in the proof, because this is a proposition. It's that we prove with Atul and John. And the proposition goes as follows. You start with topological graph with a compact vertex space, and we want to have an isomorphism. We want to show that this the double suspension of a topological graph C-star algebra is a topological graph C-star algebra of a double suspended graph. So hence the name, and that's if this doesn't work, then our construction is not great. So the idea of the proof is this. First, I'm reminding you of this decomposition of our correspondence. So our correspondence looks like this, and the idea of the proof is as follows. We will define something that will be a representation. So if you never see representations of correspondences, you'll see one in a second. And then we'll check that it's covariant. If you have a covariant representation, you'll get a map that will go from the C-star algebra of this correspondence to this C-star algebra. And now you can check on generators that it will be surjective, and then you use gauge invariant uniqueness theorem to prove that it's injective. So that's the idea of the proof, and some formulas. So first you have to make sure that you satisfy the relations. So you write down the formulas this way. So first on A, so phi 0 will be a star homomorphism. So you extend it from this formula to a star homomorphism. And so delta W goes to 1 tensor PV, like this part goes to here, and this part goes here. Right? And then so on this TE0, it's supposed to be this tau on this previous slide. I'm sorry for that. I prefer this notation to the tau. So I wanted to change that before, but I forgot. So we have those two formulas, and then you can just check by hand that the relations are satisfied. So first of all, it's well defined because of the relations on the Toeplitz algebra, because remember that this algebra is just tensor product of C star of E and the Toeplitz algebra. So using the relations in the Toeplitz algebra and using the fact that T0E and T1E are a representation, this universal representation, you can prove that psi 0 and psi 1 give you a representation. So phi 0 is a star homomorphism, phi 1 is a linear map, and they satisfy a compatibility condition with the inner product, but this all is thanks to the same conditions satisfied by this universal pair and the relation to the Toeplitz algebra. So you get a representation, and now to prove that it's covariant, you need compactness of E0. So here where compactness of E0 is really important, because you want to prove that this W, W is a regular vertex, right? So you're looking at this W, and the things that you want to find a compact neighborhood of W such that did I write it correctly? I was looking at the source map. Sorry, let me go to the. Oh, sorry. Here's the source map. So we want to prove that it's regular. So first prove that it's finite. So we want to find the neighborhood such that the source map, preimage of the source map is compact. And then we're using the fact that every element of E0 starts in this source map. So that will be our compact neighborhood. It's W plus E0 is the compact neighborhood we want. Right, so this gives you finite, but then also you can show that it's non-empty. So this gives you regular. So let me go back to the proof. So we use compactness to make sure that we get covariance of this relation by, and I didn't say what covariance mean, but this is just an idea of the proof. So the idea is that to get this special kind of representation, you use compactness, and then if you get it, you have a star homomorphism, which you can prove is surjective and T equivariant for the action of the circle. And then gauge uniqueness theorem implies that it's injective. So that's the whole idea. That's the proof, and it's different than the proof of Szymański for graph algebras. We couldn't just simply copy paste their proof. We have to use the tools that we had. So we use the representations and C-star correspondences. And now, if you notice, the example of the quantum ball. So, but first, let me maybe stop for a second in case there are any questions about this.
I have a question.
Yeah.
If you can go to the next page.
To the next page.
Oh, no, it was the previous one. Yeah,
this page.
If E0 is compact, then adding a single point, which is disjoint with E0, reminds me the one-point compactification of a space which is already compact.
Yes, exactly. Yeah.
So, can you visualize somehow the structure, geometric structure of your construction in terms of first some cylinder and then compactifying it by resulting in adding this point, this W?
So let me do something better. I'll just give you an example where everything will be visible, what happens.
Okay, thank you very much.
Yeah, of this quantum balls. So you can see how this construction really works. So the odd dimensional quantum balls are exactly defined, can be defined inductively by this quantum double suspension. And here, of course, there's Q, but in this definition, Q plays no role whatsoever. But you can prove that if you define quantum balls by Janus-Thiessen relations that are Q commuting and so on, for Q from 0, 1 different than 0, different than 1, sorry, that all those C-star algebras are isomorphic. So here we're using this fact, and we're actually, this is the original definition of Hong and Szymański. This is not my kind of a shortcut. It's the original definition is just inductively by quantum double suspension. And you do the same for the even quantum dimension balls. And you can also prove that odd dimensional Waxman-Seidel quantum spheres can be defined this way. The same for even dimensional quantum spheres. So you have this construction. And let me tell you this one comment that it was actually, for some reason, I mistakenly believed that you cannot see odd dimensional quantum balls as topological graphs. And if not for Atul and he's just perseverance and just like showing me that this can be done, and he was not discouraged by me saying it cannot be done, and now I feel kind of bad. But he was the first to get this idea, and then we proved the theorem I showed you before, this proposition together. So the idea is as follows. We first of all, the first observation, they are not graph algebras. You can prove they are not graph algebras. And now, however, with topological graphs, we have this additional feature that functions, commutative C-star algebras can be defined using topological graphs. Very kind of degenerate topological graphs with no edges, right? So you just take vertices to be the space you want to get the isomorphism with, and then 0 edges, and then empty maps here. It's a perfect topological graph. And its algebra is isomorphic to the algebra of the C-star algebra of the space you're working with. So now this is something you could not do with graphs, right? So now we have the 0, 1 interval, and now we can do this construction, and we get this picture. And this is, of course, only a visualization. Here you have this interval from -1 to 1, and then you have this added 1 vertex, and we have this edge, this loop that we added, and all edges going here. So of course we have a lot of ... because this is actually a compact set, again, of those edges. For every point here, there's one edge. But we're just visualizing it this way. So the quantum balls, this is 3-dimensional quantum ball. It looks like this. Okay, and I find it very, very beautiful.
Mariusz, may I ask you, your theorem here about this commutation of a quantum double suspension with taking the C-star algebra, You do it in the context of topological graphs, but would it work also for discrete graphs as a subcase?
Yes, I was actually mentioning that it is known for discrete graphs because we are generalizing Hong-Szymański. So
Hong-Szymański did it for discrete graphs,
exactly.
right?
Yeah. I was saying that. So they did it for discrete graphs, and we're doing it for topological graphs. However, their proof we had to change the proof because somehow the just graph proof didn't work as well. So we use a different approach, but it will work. Our proof, of course, is like an alternative proof to their result as well. Yeah, but for graphs with finite vertex set. So this is the first nice picture, right, of the quantum ball, and then the second nice picture will be of quantum spheres, because I was telling you that the on-dimensional quantum spheres, the Waxman-Soibel quantum spheres, can also be defined this way. And here we have a nice twist because C of t is one of the very few commutative C-star algebras that you can get as graph C-star algebras. That's why those algebras are graph C-star algebras, right? Oh, this should be S here. Sorry, this is a typo. So this odd-dimensional spheres are graph C-star algebras. However, now with our construction, we can also have a topological graph for quantum spheres, and it looks like this, right? We have a circle now, and we have a lot of edges, like another compact set. This is just a visualization, right? And then we have this one additional vertex with one loop. So this is how you can view now odd-dimensional quantum spheres as topological graphs. And of course, if you iterate, you just add more loops, and then you have this, you're just kind of repeating the same pattern. You're just adding another loop, and then you will have to have also an edge from this loop to this one, right? And so on and so forth. It's exactly the same as for usual quantum spheres and their graphs. So now it's a very nice picture. So for the quantum balls, by the way, also those pictures were made by Atul, not me. So I'm not taking credit for the pictures. And so now this is what we found, and we have this example. This is something that is nice because this was something that was missing from our program of those push-out to pullback theorems with Piotr. We had even-dimensional spheres, but we couldn't do anything about odd-dimensional spheres because odd-dimensional balls are not graph C-star algebras. But now with topological graphs, we can finally have some of a graphical picture of the pullback of odd-dimensional quantum spheres, right? So there are, of course, some natural surjective homomorphisms and a pullback diagram like this, which is just showing you this kind of like a quantum CW complex structure of odd-dimensional quantum spheres. And this pullback diagram, this was also proved that this pullback diagram exists, and that the diagram exists. This is pretty easy, but then that it's a pullback was proved by Hong and Szymański as well. So this kind of a picture we didn't have from our theorems and from like push-outs of graphs. And this is I'm coming now to the second part of my talk, is that now we have this picture, right? That we have this interval 0, 1, interval 0, 1, and then we glue them over the Podlesh sphere graph. So we have those two elements, and then we glue them to a circle, right? And that's how you get this very nice picture of a kind of push out of graphs, or like a union of graphs, by gluing over subgraph over their intersection. We're getting this new topological graph, and this is for 3-sphere. And I remember that for the 2-sphere, for the Podlesh sphere, this picture for the same picture, but for the Podlesh sphere, was the kind of starting point for us with Piotr to start this few years before this project of when can you actually have a situation when you have like a push out of graphs, when you can have a pullback of C-star algebras. And here I view this like a nice motivating examples to do the same for topological graphs now. right? We're starting with this very simple one, and it looks like, at least on this picture, that this is really a gluing, this is really a push out. And we know from other sources that actually the diagram on the Algebras is a pullback diagram. So now we have this whole push out to pullback theorem.
Sorry, can I just ask a quick question?
Yeah, sure.
So in this push out of graphs, what are the morphisms in the category of topological
That was
graphs
exactly
that
my question too. Yes.
Yes, exactly. So this is just like a motivating example. Right now, I'm just looking at this and I'm saying, wow, it really kind of works, right? And then what are the morphisms that help you do this, and what are the actual push outs you can do, and how far you can from just looking at this picture and seeing, well, of course, this looks like a gluing, to just precisely saying that this is a push out of graphs with appropriate morphisms. So I'll tell about it in a second. So
let me quickly comment. You see, here it's a very simple push out, because in a way it's a union, right?
Yes, yes.
You just have a union, so everything is injective. So the idea is to have like admissible subgraphs, and then take the union, right? So well before the general push out to pullback theorem was developed by MARIUSZ and myself, and also, just MARIUSZ and myself, then first we studied in depth a much easier situation when, instead of more general push outs, where you really have to define what you mean by morphisms, we just were working with what are admissible subgraphs, which to a great extent was already done in the literature. So we had only additional conditions so that such a gluing makes sense. But it is in general a very tough question. What is an appropriate category of graphs? And it takes years and years of development to have everything really fine-tuned.
Yeah, thanks for the comment. It's so for now, this is a very kind of like an easy situation, but I was trying to, just have the story of the talk like this, that first we have this example, and now we're looking at this and we're kind of now motivated because we saw in the real life that it might happen, that you have something like this, and then how far you can go with this program now for topological graph. And the program is this: suppose you have a push out in whatever with whatever morphisms in what category of topological graphs. When do you get a pullback of respecting topological graph C-star algebras? And now the topological case is, as you can imagine, is tricky, because for push outs of graphs, you just take these are just sets and set maps, and so you just take. For pushouts of graphs, you take respective pushouts of edges and vertices, and then somehow you define the source and the range map so that everything agrees, and you always get, at least for the category, let's say, of graph homomorphisms, so the homomorphism that intertwine source maps and range maps, it's easy to have an idea of what pushouts are. But here in the topological case, we have obstructions, because pushouts of locally compact Hausdorff spaces might be neither locally compact nor Hausdorff, right? So then, and my starting point from this, the first slide was, let E1 and E0 be locally compact Hausdorff spaces. So I have to somehow overcome this. That's the first thing. And also, even if you take unions, it's very easy to imagine that if you take a union of spaces, it doesn't have to give you a push out, because only in this situation when both are open in this bigger subspace or both are closed, you get a push out. If one is open, one is closed, you can just not get a push out over the intersection. So there are many new things coming from topology, but also this is exciting, because like pushouts of graphs, they're all nice, but this is all happening over a discrete set. You're not having any cool gluings, and here you can use all the power of topology and quotient maps and really have gluings and pushouts. So this is really exciting. However, there are some obstructions that you can. So immediately you go to adjunction spaces. So one injective pushouts. This is to get.
Sorry, Mariusz, I'm having troubles visualizing when somehow the union or, double injective push out of locally Hausdorff compact spaces, locally compact Hausdorff spaces would not be locally compact Hausdorff.
So it should be examples like intersect an open disk with a closed disk, and then the intersection. It will be one way that is, I think. I'm just trying to. Oh, so one thing is that it's really. Sorry?
Maybe two disks.
Maybe two disks, yeah. So intersecting an open disk and a closed disk. And then I think the intersection, because the problem also is the following. Now we want to have locally compact spaces. So we want to look at proper maps. So we would like everything to be closed, if possible, as subspaces. That would be another abstraction. But first, let me I had this example somewhere. Okay, maybe let me retract this comment, because I'm pretty sure that I know how to do this. I'll not figure it out just during the talk. But
can I add something quickly to this?
Yep.
So the push out of Hausdorff spaces, if you can make it Hausdorff by remaining ambiently in the category of Hausdorff spaces. In the very worst case scenario, you're doing this in top. And if you did some kind of push out and you get something non-Hausdorff, if you only want to consider functions into Hausdorff spaces, you can then just quotient out by the non-Hausdorffness. This is a left adjoint to the inclusion of these, and so you'll preserve all of the information so long as you only consider going to Hausdorff spaces.
Yep, exactly.
So you're saying there is some Hausdorffification.
Yes, exactly. Hausdorffification. That's true. But so I'll be remedying it differently. So I'm not quotienting out about Hausdorff, like non-Hausdorffness. I'll have assumption on my push out so that I always get a Hausdorff space. And the assumptions are that I'm looking at adjunction spaces, so or one injective push outs. And with one of the injections being a close embedding. So let me maybe specify what do I mean. So there's this proposition, it is surely well known. However, I couldn't find any proof of it, so we reproved it, that if you take two locally compact Hausdorff spaces and A is a closed subspace of Y, and then your attaching map is proper, then the adjunction space corresponding to this, so this one injective pushout will be a locally compact Hausdorff space. But you need properness of F and you need closeness of Y. So closeness of Y gives you Hausdorff, and then properness of F gives you locally compact. So this was so in a sense, in a way also, and this is for Piotr, it kind of justifies our work on the one injective pushouts always, right? Because if you go beyond just graphs, go into topological graphs, you immediately have to look at one injective pushouts to remain Hausdorff, and then you look at proper maps to get locally compact Hausdorff space.
Yeah, I mean, for us, these one injective pushouts were necessary because we needed proper maps, which means in discrete topology, finite to one.
Exactly, yes.
But this category of proper maps is not closed with respect to taking pushouts. So if you take a pushout of two proper morphisms, that's not in this category, because the induced morphisms by the pushout are no longer finite to one, unless you assume that at least one of the maps is injective. So
exactly.
One injective, one finite to one, the resulting pushout will be again injective and finite to one.
Yes, and the same happens here, right? So it's like a similar phenomenon. Yeah. So a non-example would be this. So you take so you can see that it can very easily go sideways. So you take a compact space X, just the sequence and its limit, right? And then for A, for Y, you take X times natural numbers with discrete topology. A is your closed subset when you only take 0 and n. And this map F is not a proper map. And now your adjunction space, I don't remember, but it's somewhere in Engelking or some other topology book. It will not be locally compact, right? The adjunction space. Still, it will be Hausdorff because it's a closed subset, but it will not be locally compact. So you really need properness of F, because you can have the non-example like this.
I have a linguistic question. What's the difference between counterexample and non-example?
Oh yeah, sorry. That's a good. I deserved it. Yeah. So, a non-example is you get an example that is not satisfying the assumptions of a proposition, and therefore it will not also satisfy the result. So you get a
counterexample.
Yeah, which is a counterexample. Okay. So
I think the difference is a counterexample requires you to assume something that's false.
Yeah.
Okay.
Yes.
Whereas
yes.
a non-example is just
Yeah.
I'm not assuming the truth.
Okay.
Okay.
Yeah. I counted on you to give an answer, in fact.
Glad I could provide.
So okay, so can we sell? Is this a non-example or a counterexample?
No, it's a non-example.
Non-example. Great. So I don't have to change my slides. Okay. Now morphism of topological graphs. And here we are very lucky because we already have the answer, the right category of morphisms defined by Katsura. And a quick story is that we found those morphisms when, together with Piotr, we were working on the definition of the right morphisms just for directed graphs. And it turned out our conditions were exactly the same as Katsura's conditions. Well, of course, the definition of regular vertex space, for example, is different, but the phrasing is exactly the same. So, and I'm not changing the name. Katsura calls it a factor map. I will do it so I'm also calling it a factor map. So we take two continuous maps between edge spaces and vertex spaces. We have two graphs, and those maps have to satisfy this first condition, which is the condition of having a graph homomorphism, so intertwining range and source maps. The second condition is that those maps are proper. So in the original definition of Katsura, he's looking at maps from the one-point compactifications of your locally compact Hausdorff spaces that put infinity to infinity, but that's equivalent to having a proper map. Before you took this one-point compactification. So we have properness and graph homomorphism condition. And the third one is something that we call with Piotr target bijectivity condition or range bijectivity condition. And I'm just phrasing it in the way that Katsura phrased it. So this is really, but what this means is that if you take a pair, an edge in F1 and a vertex in E, such that they have the same, the range of X is M0 of V, then there exists exactly one element from E satisfying M1 of E equal X and RE of E equal V. So one way of viewing this is that, in fact, when you write a diagram for the range map, right? So you go from E1 to E0, and then you have the range map from F1 to F0, and then you write the maps between the edge spaces and the vertex spaces. This diagram has to be a pullback diagram in the category of topological spaces, even, right? So you get a fiber product. So now E1 is a fiber product of F1 and E0 over maps RF and M0. This is basically what this point 3 is telling you more categorically. But if you just want to check it just on points, this is how you do it. And now a factor map is called regular if the following condition is satisfied. So preimage of regular vertices are regular. And this.
Mariusz, if you allow me just one quick comment,
Sure.
I cannot resist it. You see, when you speak bijectivity, then it means surjectivity and injectivity.
Yes.
Okay. And now we have this new paper with Gilles and Francesco about relation morphisms. And very surprisingly, at least to me, I don't understand it conceptually why it happens. I mean, it's proven, it's computed, okay? It turns out that in order for a relation morphism to induce a homomorphism between the path algebras, properness is not enough. We must have target injectivity.
Mm-hmm.
Okay, that's necessary, and this is kind of funny because we don't have it at this level here, right?
Yeah.
So somehow that condition splits into two subconditions, and for me this is very tantalizing. Just a quick comment.
Yeah, this is very interesting. Yeah, thanks for that. here we have bijectivity, right? So, and also why this condition is exactly the same for graphs. Well, that's because the range map is a local homeomorphism. So you have this discreteness on the pre-image of the range map. So this condition 3 is exactly the same for graphs as for topological graphs. So you don't have to change a thing. So the only thing you're changing when you go from graphs to topological graphs is the definition of regular vertices and the definition of properness, because now it's about compact sets and not finite sets. Okay, and now examples.
So, may I have a question? I have a request. Could you write down this pullback version of
yes,
condition
exactly.
number 3?
Sure, you're right, because this condition, it's nicer to just see it. So we have E1, right? Then we have the range map, range E goes to E0. Then we have F1, you go to by range F to F0, and then we have M0, and then we have M1. And I'm saying that this diagram is a pullback. So it's those two maps, you're taking a pullback of those two maps, and that's your E0. That's your E1. And it also works in the topological case. This is something I also checked, that this topologically it also works. It's not only for sets, even though this is, but there's this, the maps are continuous here, M0 and M1 are proper. That's how you can still prove that E1 is a pullback now in the category of topological spaces of those. So it's a fiber product if you want.
Yes.
And the very big upshot of this presentation is that now you can see that this condition is composable, because composition of pullback diagrams is a pullback diagram.
Yeah, you take another graph. No, not this way. I think it's here. So you take another one. Yeah, it's take another one, and then you can compose them. And if this one is a pullback and this one is a pullback, then this one is also. So the outer one is a pullback. So this is very nice for proving that you have actually can compose those morphisms. You can call them morphisms, and you really get a category of those. Okay. So
but I'm puzzled. How about the source maps? Because this is such a natural condition, and we obviously do not need this pullback condition for the source map. And I'm just wondering, what would it bring to the game? I mean, what advantages would we have if we put this additional assumption? Because it's so natural. I mean, it's
exactly.
This assumption is so very natural.
Yeah, you're right. I don't know. I think I had the same ideas. Like this was also like kind of curious. I was curious about this, and I tried to prove something, but now I don't remember if I had any conclusions. But it's something I would like to check.
Sorry, but this correspondence encoding this zeta algebra is not symmetric with respect to range and source.
Yes,
of course, it is
because
not.
the regularity does the job. So thinking about the source corresponding diagram is not necessary.
I know it is not, but I'm just curious if such a condition would play any role. I mean.
Yeah, but
it's reverse engineering. You have this pullback property for the target map in order to preserve the first Kunstkrieger relation, and the second Kunstkrieger relation is preserved because of a regularity condition.
Yes,
so that I know it's reverse engineering. That's how these conditions were derived, in fact.
Yeah. Okay. So let me maybe, because I have like 15 minutes or maybe less. So let me maybe go.
Yeah, you have 12 minutes. Yes.
Yeah, 12 minutes. So at least I would like to write down the main theorem. So let's try to do it. So examples from directed graphs, everything we talked about with Piotr, everything there's already in our paper on that was accepted in the Journal of Noncommutative Geometry. And it's on arXiv, so you can take a look there. The paper is from length preserving pushouts to gauge invariant pullbacks, something like that.
Yeah, something like this.
Something like this, but It's a long title, but so
and it's a long paper.
And it's also a long paper, yeah. So just to give you a different flavor, an example, just take two spaces, X and Y, and let's say I have two homeomorphisms. Then if I take F such that it intertwines the homeomorphism, which is just saying equivariant for the integer action on both of them, then you also have a factor map. And here, this example is very easy because all edges are regular. So regularity you get for free. And you don't have any non-regular vertices in the examples coming from homeomorphisms. You have to take F to be a proper map. So I forgot. So you want to have a proper map from X to Y. So I forgot to write it down. So if F is not proper, then it will not work because your M0 and M1 will be this F. Right? So this is a kind of a different example. I'll give you also an example of a subgraph, now say regular closed subgraph of a topological graph here. So first, and I'm splitting this into closed subgraph and regular closed subgraph because I'm going to need this in my theorem in one of the propositions. But so a closed subgraph, and now we have to, this was something that was not possible for graphs, right? Because then you have discrete topology. Here you have.
I mean, it was possible. It was just vacuous.
It was just vacuous. Yeah, you're right. You're right. Now open and closed play a role, and Katsura looked at open subgraphs in his paper. Here we're looking at closed subgraphs. Open subgraph corresponds to some subalgebras, and I think you have to take it's in the second because so Katsura had 3 or 4 papers. No, I think 4 papers when he first defined those topological graph algebras, and there's a series of 4 papers, very nice papers. And in the second one, he's looking at open subgraph and defines factor maps in the second paper. In the first paper, he's proving the gauge uniqueness theorem. In the second one, he's looking at factor maps, open subgraphs. In the third paper, it's about ideals and ideal structure and so on. So now we're assuming closed subgraph, it's just you have closed embeddings and you satisfy the condition 1, which is the graph homomorphism condition. Now, to have a regular one, well, you want to have a factor map, right? So closed subgraph is a regular closed subgraph if this M that defines those 2 closed embeddings give you actually a factor map. So you satisfy condition 3 and you satisfy condition 4, and you have and properness you have for free because closed embeddings are the same as injective proper maps. So that's fine. Now examples would be admissible subgraphs of directed graphs that we defined with Piotr. And now here, a nice example is that if you take a subspace of your space X, so closed subspace of X, that is invariant with respect to this homeomorphism. So phi of A is inside A, then this will give you a regular closed subgraph of E. So G would be a regular closed subgraph of E. And now for this very kind of a strange example with R and the absolute value, just take this. And here there's something interesting happening because this G1 0, I should have just written down G1 equals G0 equals this. So you just have one edge and one vertex, and this vertex will be a loop, right? Because source and range map of 0 is 0. So you get, so this graph G1 is the graph, is just loop. So it's C-star algebra is the functions in the circle. While this, we actually didn't compute the C-star algebra. It seems to be nothing like known or very interesting to I mean, it is interesting, but it's not something that immediately you know, oh, this algebra is this. So it's not an algebra that I know, for example. So so you take this source map, and this vertex is regular in G1 in G, but it's not regular in E. But this is permitted. You only have to, so singular have to go to singular, a regular can go to singular. And this is a very nice example when a regular vertex go to this new singular type of a vertex. So it's not going to infinimeter, it's not going to a sink, it's going to this boundary of the sink. Right? So this is an example that I really like. And a proposition is that if you look at the image of any regular factor map, it will define a regular closed subgraph. Yeah. And this is something that we did not do for the directed graphs, but this is a natural question, and you can get a closed subgraph just on the image, just for using the regularity of the factor map. So a factor map might not be injective, so it might glue some things, but the conditions like the target bijectivity conditions tell you that you cannot glue things that will then kind of spoil regularity of this closed subgraph. So this is important for the theorem, because I'll be using the fact that the image of a factor map is itself a topological graph, right? And to prove that M1 of G1 is that you're getting this target bijectivity condition, well, you use you use the fact that M1 satisfies the target bijectivity condition that you start with. Okay, let me go through the definition of a junction graph. So very quickly. So now, if you have two topological graphs and you have a closed subgraph, and now these are assumptions that are fine-tuned, so I can get a locally compact Hausdorff space in the end, and the topological graph. So my assumptions for now are that this closed subgraph is not regular, but it satisfies target bijectivity condition, right? And then the maps here are maybe not regular, but they satisfy conditions 1 and 2. And this is enough to get the topological graph. And what is the definition? First, also, let me remind you that this P0 is a very natural map from, if you have a junction space from F0 here, there's a canonical way to do it there, induced by M. And the definition is as follows. Of course, both edge space and vertex space, you take the adjunction space, and then the source map and the range map, you define like this. Here, there is a difference between source and range, and this difference is coming from the fact that I'm assuming this about the range map. And this will be needed because this just means that kind of there's some sort of disjointness about this range map. Things in E1 go to E1, and then things outside of G goes to things outside of G. And so there's this thing that I want to incorporate already in the definition, so it's easier to prove that you get a local homeomorphism. Right? Because so this condition helps me, the kind of disjointness helps me to prove that I have a local homeomorphism based on the fact that RE and RF are local homeomorphisms. For source map, there might be some edges that say begin in G but end outside of G. So I have to put them by this P. I have to put them here in the space. And remember that I'm thinking about E1 as a closed subspace here, and and this as an open subspace here. So you can prove for adjunction spaces when this subspace G is a closed subspace, that this will be a closed subspace of this space, and this is an open subspace. And as sets, you just get this disjoint union of those two sets. But the topology is not the topology of the disjoint union, right? So that's how you get this gluing and junction. Was there a question?
Well, I have a question.
Yeah.
What is who did it? So a junction graph, is it your baby with Atul or?
Yes, I didn't write this, but this is our definition. Yes.
Okay. And now, why do you call it a junction, and what is it in the case of discrete topology?
Yeah. So first of all, we call it a junction because there's this well-known definition of a junction space in topology when you do exactly this, right? So that's why you call it a junction graph, because and you have this attaching map, and those junction graphs are used in K-theory, right? Because they are basically just one injective pushouts where you assume that one of the injections is a close embedding.
Okay.
And for me, it's just kind of nicer, because in some books on topology, you will not see pushouts, but you will always see adjunction spaces.
Okay.
Right? So it felt a bit more natural to talk about this. What we mean is, of course, one injective pushouts, and we want to define the source and the range maps in such a way that everything works. And this can be done, and you can prove that if you define it this way, it is a topological graph. The main part is, of course, to prove that R is local homeomorphism. Because everything else, that those spaces are locally compact Hausdorff, this is taken care of by assuming that M1 and M0 are proper. So these are locally compact spaces by this other proposition I had, right, about those topological obstructions. Okay, now here are some propositions. I don't want you to look at them because I don't have too much time, but those propositions are just...
Well, you have exactly -3 seconds.
I have exactly -3 seconds. Yeah. So these are some propositions that we were just struggling with proving the result that we had with Piotr for directed graphs. That if you assume in these adjunctions that, let's say, G is a regular closed subgraph and M is a factor map or a regular morphism, does it follow that those other maps, that this inclusion of E1 give you a regular factor map, and this P0 is the regular factor map? And this we couldn't prove. It was not possible to just generalize the proof. So we have some conditions for which it works. Everything is good for properness. Everything is good for graph homomorphism. Target bijectivity, that's fine. The proof is the same. But regularity is tricky. And for regularity, we only know that if one is regular, then the other one is also regular. And this is the story here. So now, this is just the theorem of Katsura, that if you have morphism like this, then you have a map between algebras. Right? So this is just this slide is not too important. It's just saying that factor maps were just defined to get this contravariant functoriality from graphs to C-star algebras that have an action of a circle. And now the theorem is as follows. So the adjunction graph, and I'm assuming that the G is a regular subgraph, that M is a regular factor map, so it's an admissible morphism. And I'm assuming also at one of the two, either that E is closed or that this P is a admissible morphism. And if you have this and this one additional assumption, then you get the pullback theorem. And this additional assumption is exactly in the case of discrete graphs. It's actually, it's not stronger. It's the same as our assumption that we had with Piotr about breaking vertices. Because singular vertices, they have infinite vertices and this closure of the sink. So if you look at this intersection, then you have regular intersected with infinity meters. These are breaking vertices, right? Regular for the subgraph, but infinity meters in the whole graph. So breaking vertices in one graph cannot be also breaking vertices in the other graph, which is this F.
Exactly.
Right. So this is how you generalize this. However, in case of, if you would just take this condition about those breaking vertices and try to prove it, then it fails. So it's like for this row finiteness for topological graph, you had to kind of reinvent this definition. So here we also reinvent this condition. However, for discrete graphs, it's exactly the same, but there's this new piece of data, this boundary of the sink set that is giving us problems. And just this last thing I wanted to say, this is a work in progress. This is a disclaimer. This might be, there might be some more assumptions, too many assumptions, or maybe we need to add something more, or maybe too few. I was looking at this before the talk for the last week. It seems to me that it's okay, but it's still a work in progress. You never know. And now the last example, and this is the example when you have this real line with the so our graphs here are this. Wait a second. So our graphs are, I'm taking E1, E0 to be this real line with a source to be the absolute value, and the same for F. So we take two graphs, it's a union actually, and here also the source is the absolute value, but you have source for E, source for F. And we take a union of those two things on the plane. And now this red arrow, this red loop, of course, it doesn't kind of exist here because G is not this 0 for each of those graphs. It's not regular, but for the intersection, it's regular. And then that's how you break our condition. For our condition was that E0 singular intersected with G0 regular should be in F0 regular, but it's not. because this point is not regular in both F and E. So it breaks our condition, although everything here is finite, no breaking vertices, right? But it breaks our condition, and then we prove with a tool that this is not a pullback. And the proof, of course, I'll not give you the proof, but it boils down to something I had as a problem in one of the classes, that you have to find a function that is zero, that is vanishing at infinity. It's zero here, but non-zero everywhere else. So take a function like this. And this function proves that this is not a pullback. If you go, but this is just like a very, this is a cheating way of doing this, but I found it really nice that a problem that I had in my class was solving this also. And with this, I'm going to finish my talk. Thank you very much for your attention.
Thank you so much. Well, for me, it was a very beautiful and exciting talk. So let's do the questions. Tomek, Dimitri.
Yes, I have a question. For discrete graphs, you have the notion of hereditary and saturated
yes.
assumption. How would you modify it in this topological context?
So it's in the original paper of Katsura, when he was classifying ideals, instead of defining hereditary saturated subsets, he was looking at complements of them. So it's which for me is just better. So I'm looking at this. So instead of hereditary saturated, which is I'm looking at let's take subspaces of my vertex set, and I'm saying they are positively invariant or negatively invariant. And positive invariance is, and this corresponds to a complement of the hereditary set. So positive invariance is that if there is if source, I have to think. I don't want to make a mistake. So positive invariance, I'm just gonna take a look at my notes, because the problem is that Katsura is using a different convention that I'm using. So I'm always struggling if I'm using my convention or his convention, so to make sure that I'm not making any mistakes. So if the range of some edge is in X0, then this implies that the source is also in X0. And that's positive invariance. So that's kind of like complementary to hereditary. And this is enough to define this. And then negative invariance, so the saturatedness, is this, that for any vertex V, which is in the intersection of X0 intersected with E0 regular, there exists some edge in E1 such that source of this edge is V, and the range is also in X.
So this is the same condition as in the discrete case, except the definition of regularity.
Exactly. Yeah. So this is very similar. However, I'm happy about this question because I wanted to advertise this approach because I like it much more than hereditary saturated subsets. It's because we were always when we were working with Piotr about this, we had subgraphs, and then we had to look at complements of those subgraphs, and it was just to have all the results in the same way, written the same way as in the graph system algebra literature. But if you use Katsura's convention with looking at complements, just positive invariance, negative invariance, and you can also classify all ideals with those. So for row finite graphs, it's enough to have this X0. For non-row finite graphs, you have to have also a new subset. So you take two subsets, X0 and some subset Z0 here. And I think you want to assume also to be x to be closed, x0 to be closed.
Okay.
Yeah. So and then you classify ideals now with pairs. It's like hereditary saturated subsets and this breaking vertices. That would be for graphs. But here in Z, you can have now things like here. Vertices that are not breaking vertices, but still they're singular, and they're troublesome when you want to look at quotients and those quotient graphs or whatnot. So hereditary saturated, you can do this, and in the paper of Muley and Tomford on topological quivers, they do all of this, but for hereditary saturated subsets. Right? So in the the two approaches are complementary. I just prefer the one of Katsura because it's for me it's much easier to think about this instead of hereditary saturated is positive negative. For me, this is better.
So the Z0 is related to this Katsura idea.
Yes, but no. Wait. Katsura ideal for. So Katsura ideal, if you want to know, Katsura ideal for graph correspondence, these are just functions on the regular vertices. So Z0 is actually not related to I mean, it's related. It's related in the sense that it's not a regular vertex. It has to be outside of regular vertices, this Z0. It's in between singular vertices here and so I'm not making any mistakes. Let me take a look. And intersection of x0 of singular vertices in E0. So you can think about two possible ways. If you take this subset X, in this example that I have this picture here, your X can be just 0, but then you have two choices of Z. So one choice is in an empty set, and the other choice is again 0. So that's how you get two ideals corresponding to two pairs, even though there are no infinimeters, there are no breaking vertices here, but still ideals, there are some ideals that are not classified just by X's, just by hereditary saturated subsets. You have to have this additional information, this set Z. And this example shows you how this can happen. So
sorry, but still it's not clear to me what is this dichotomy between this Katsura ideal and Z0.
So I would have to...
They are of complementary nature.
No, I just said...
I see that the Z0 is not unique.
It's
while
not.
The Katsura ideal is unique.
No. So if I said at some point that there's any connection, I wanted to say there's no connection. Okay. Because the Katsura ideal is a unique ideal, and it corresponds for the topological graph. It corresponds to just regular vertices, yes. Right? While Z can be for given X, you can have many Zs, right? So it's very non-unique. And in this example, we can take empty set or 0, and you get two different ideals, gauge invariant ideals of your C-star algebra. So and there is a way, of course, as for graph C-star algebras, from hereditary saturated subsets, you go to ideals, and the same you can define it here. It's a bit more complicated in the topological case, but still the gist of it is the same.
Mm-hmm. Okay, thank you.
Anybody else? Dimitri, go ahead.
So, thanks for the very nice talk, Mariusz. A more structural question is: do you know any criterion for pure infiniteness?
Good question.
Yeah.
For directed graphs, it should be something about the path space, like it's no isolated points. Can you make sense of it in this context?
So it's a great question, and I can only give you a reference. I was never studying, but this is the fourth paper of Katsura. It's called Pure Infiniteness of Topological Graph Algebras. So there are 4 papers on this, and the fourth one is about pure infiniteness. And he gives some conditions, but I actually never read it in detail, so I don't feel in a position to talk about this, but at least I can give you a reference.
Okay, thanks.
Gilles?
Yes.
Maybe. Sorry.
Just I guess a comment before my question is that the Katsura ideal is actually 0 in the topological graph sister algebra, because you mod out this ideal from the topless algebra to the
yes, of course. Yeah, but so I was saying that this Katsura ideal is an ideal in the algebra of the vertex space, right? So yeah. This is an ideal here.
Contains, yeah.
But there, of course, maybe I said something wrong, but so JX is not an ideal. It's exactly 0. This is the part that you quotient out when you define the topological algebra, graph sister algebra, right? So I didn't have any time to talk about the construction, but this is the main point is that you quotient out by this Katsura ideal. So Katsura ideal is not an ideal of the topological graph sister algebra. It's an ideal of the vertex space, right? And it actually is 0 in the topological graph algebra. So on the left-hand side, I was talking about gauge invariant ideals of the algebra, and they are connected to X and Z. So there is a connection between the admissible pairs, so X and Z, and gauge invariant ideals. But the Katsura ideal is an ideal in a different algebra, and it's actually 0, as Gilles pointed out, in the topological graph algebra.
So my question is, have you considered path morphisms for topological graphs?
Yes, it was also my question. Yes.
Yes. So I was I only very briefly I looked at it, and it's on like a to-do list. It seems to me that it should be very interesting for the topological graphs, because then you have this Fock representation on the path space. And then I think the conditions we had for directed graphs, for path homomorphisms, they should somehow be visible in this module structure. But I don't know for now anything about this. I didn't look at any conditions. And because our regularity condition for path homomorphisms, it was something that I was struggling with. Piotr can tell you for a very long time, and I still feel like I'm struggling with. So that's why I didn't look at this for topological graphs for now. But for sure, I'm interested in this.
Yeah, because then the next step would be relation morphism for topological graphs.
Yes, exactly. So I have this very crazy idea about relation morphisms that. Let me only write it down, that you can take the Fock space for a graph E, let's say, and let's this E star denote the path space. And you can take this Fock space for this other graph. I was thinking about taking like a tensor product of them, and then looking at this as a bimodule. And there's this notion, and John Quigg and I think Siegfried Echterhoff, I probably mispronounced his name, but they have this category of modules on as morphisms of sister algebras. And I'm naively thinking, and this is maybe not true, but I'm naively thinking that our relations have something to do with this module being an appropriate module in this category. This would be very nice, but I might be this might be a wrong intuition to have. But those modules are an infinite path space, so it's like taking relation would be maybe some quotient of this. I don't know, but because if you take those modules and those morphisms, you look at classes. You don't look at the module itself. You look at classes. So I was hoping that maybe the morphisms in the sense of Quigg and Echterhoff, I think maybe also Williams and some other people, that this would be connected to our relations. This would be very nice, but I don't see for now how to even, I can only write this and speculate.
I mean, it doesn't look wrong to me, right, Gilles? It looks as an okay idea.
Yeah, another approach, I was talking to Ralph is visiting for Florianópolis, and he was trying to explain me that he has this notion of the groupoid correspondence. And if you look at the graph groupoid and try to apply his construction, we get something where I think is more general than what we did in population morphisms. I still have to decode everything he said me. And I think we could use the groupoid for topological graphs as well and try to give some kind of using his construction should work for our topological graphs as well.
Yeah, that's really interesting.
So by the way, there is a natural question. When you take discrete graphs and their graphs hysteralgebras, then they are also groupoid hysteralgebras. So how about topological graphs?
Yeah, they are as well.
Yeah. So so one thing is that there might be some confusion, because if you take a group, let's say étale groupoid, it is also a topological graph, right? But the Kunst-Pimsner algebra of this topological graph is much bigger than the groupoid hysteralgebra. It's just like groupoid hysteralgebra is more refined. It's better to work with it. But so Gilles, you're saying that there is a groupoid picture for topological graphs as well?
Yes.
Okay.
Yes.
And this is to generalize the, or to follow along the kind of Diaconal-Renault groupoid equivalent, is it? Okay.
Yeah. Okay.
You also have the notion of this boundary path space for topological graphs, and then you just take the shift map and then use the Diaconal-Renault groupoid for this shift map.
Okay. Very nice. I didn't know that.
All right, Ali.
And that's why you need, in this definition of the factor map, you need also S to take into account to get morphism on the groupoid picture, in the Diaconal-Renault groupoid picture. That. So a topological graph morphism would give a morphism in the Diaconal-Renault groupoid picture, I guess.
But I think it's the morphism not in the usual sense, that it's not necessarily a function between the groupoids, it's something different. That's what I was saying, that Hofmeister has some notion of this different kind of notion between, because I think a groupoid correspondence and then groupoid morphism, which is a little bit different than just being a function between the groupoids. But I think we can, given the spectrum map, build a correspondence in his sense.
And how is it related to the Zakrzewski stuff?
It's more general. So the Zakrzewski morphisms, or the actors, correspond to the groupoid correspondence if the correspondence as a right groupoid module is just the codomain groupoid. So similar to how a C-star correspondence comes from a star homomorphism if and only if the right Hilbert module structure is just the trivial Hilbert module structure on the codomain algebra. The same thing is true for, like, the same correspondence between star homomorphisms and C-star correspondence is what you have for Zakrzewski morphisms and groupoid correspondences.
So Zakrzewski, you're saying, is more special, right? It's degenerate.
It's more specialized, yeah.
Yeah. Okay. Good.
And the Zakrzewski morphisms are exactly the things that live to star homomorphisms. So.
Okay.
Perfect. Now, Ali, shoot, but unmute yourself. Unmute yourself. You are muted.
Yes, I'm sorry. Thank you very much for your very interesting talk, and I'm sorry for my late arrival.
That's fine.
At page 16, you introduced the third example in the page 16. You introduced a graph which you are drawing here also. Could you please? Yes. Could you please bring the page 16?
Yep, I'm trying. I had some problems.
The third example. Yes,
So,
the third example
yes.
that's I have a question about the CSR algebra of this graph. I think that it is a very huge CSR algebra because we have a lot of projection. Is the structure of the CSR algebra of this graph known or has an easy structure for description?
That's a very good question. I was looking at the CSR algebra of this graph. I don't find it easy to just say what's exactly the CSR algebra. As you said, there are many projections. It's a very big algebra. You can write down one thing that is okay is that so you're looking at just continuous functions vanishing at infinity on the real line. That's the one piece that is easy to do. But now to find the module, the Hilbert module, using this, you can write down the inner product and you can write down the norm, but it's not telling you anything, I think, very interesting. It's more of a nice example of a topological graph itself because it satisfies some conditions. And in Katsura's paper, when he introduces this example, this example was due to Katsura, he never talks about the C-star algebra. So I don't, it's not known in the literature, I think, because I was trying to see it. But I don't think it's really worthwhile to even look at the C-star algebra. It seems like a not really manageable C-star algebra.
Yes, because it has a very interesting structure of idempotent. It seems that idempotent, the space of projection is a connected space because we are generating the CS algebra by the real line. But really, is it really the case that the space of non-trivial idempotents is a connected space? So a possible starting of the problem of computation of the K theory. It would be interesting to prove that the space of non-trivial projections of the corresponding CSR algebra is a connected space, a famous problem in the theory of CSR algebra. I have another comment about this graph and the corresponding CSR algebra. This graph can be considered as the inductive limit of compact graphs. I mean that instead of real line R, you can consider the symmetric compact interval and lets them to go to infinity.
Yes.
So my question is that is the corresponding CSR algebra the inductive limit of the compact CSR algebra of the compact interval? During your talk, this question arose to my mind that to what extent the functor of assignment of the graph CSR algebra is a continuous functor. I mean that maybe one can define a kind of inductive limit of graph in the context of topological graph and ask the question if the CSR algebra of graph is a continuous functor.
Yes, so it's done. I think it's already in Katsura's papers. There's direct limit of topological graphs using factor maps. So you should be easy to check. Also, so two things about the C-star algebra I can do. You can definitely check if it's a direct limit. For that, you would need that those compact intervals, they are closed regular subgraphs in my terminology, and I think they are. So there should be no problems, including the zero, right? So you take zero and then everything. So your intervals have to go to both positive and negative direction, right? But then you take a limit. It seems to me that it might be true. Actually, I was not thinking about it. And also another thing, you can compute K-theory of topological graph algebras. So using there's a 6-term exact sequence that uses the regular vertex space. So you have this Katsura computed this, so you know how to compute K-theory. However, it's not as easy as for graph C-star algebras, where you actually just have a matrix and you can have a hands-on computation. Like this is just you have the 6-term exact sequence, but sometimes for Kunz-Pimsner algebras, for any Kunz-Pimsner algebra, you have this. But I've seen some paper when people were like, we couldn't compute it from the sequence, so we computed it differently. So it's not as easy as for graph C-star algebras. And I forgot to say that this makes our approach nicer compared to the graph algebra level, where K-theory is completely known. You cannot say anything new with the approach, this kind of like Meyer-Vittori's push-out picture here. I think there might be some benefit of this alternative way of proving it, because it might happen that the defining six-term exact sequence is not that easy to compute, and all the morphisms, the connecting homomorphism, and maybe from taking this our picture with those adjunction graphs or those push-outs, it might be easier. So for sure, you can compute the K-theory. You can check if it's a direct limit, and my guess is that it is. And then I don't know if that's saying anything about, because even if you take this compact interval, what is the algebra? I also don't know.
Yeah.
I think there's also a category theoretic accounting subtlety going on here, in that there are actually two different categories of graphs being considered in this. One is the category where you have these these regular morphisms, and it's contravariant going to C-star algebras, and you have these push-outs that get turned into pullbacks. But the other consideration, where you take the compact intervals and then you embed them into the real line, is covariance, because you're asking that you take this inductive limit that goes in the same direction as the graph embeddings, and so they're both co-limits there, whereas the other one flips a co-limit to a limit. So it's technically a different category that's being considered and a different functor.
Yes, exactly. Thank you for this comment. I forgot to mention this. Of course, yes, because you need now covariant functoriality, but it's a covariant functoriality like for graphs. Before we defined with Piotr those path homomorphisms that gave you this covariant functor, there was, of course, in the literature, there were some morphisms that people were using to have those direct limits of graph C-star algebras. For example, how to get compact operators from matrices when the graphs are clearly just inductive limits of graphs, right? And then people like Jack Spielberg and many others, they were pursuing it in this direction to have this other covariant functoriality. And for this result to hold, you also would have to have this covariant functoriality to get this direct limit. Thank you for this comment. This is important. Yeah.
Yeah, but the assumptions on the morphism are very, very, very strong. I mean,
yes. So here you can also have very, if you put those very strong assumptions, you'll get the direct limits. And I think it's in one of the papers by Katsura, like he was trying to do everything that was possible for topological graphs in those 4 papers. And they probably, it's like 200 pages for or maybe at least 150 if you put them all together, those papers. So it's a lot of information, and most of the results that you would think of that are natural for topological graphs, they are already there. And direct limits are one of those results, for sure.
Actually, the other problem that arises is that if you just think about the compact intervals and then going into the real line, that those embeddings of topological spaces don't give you star homomorphisms, just on the level of commutative C-star algebra.
Yes, exactly, yes.
Yeah. It comes from the other direction. You get restriction.
I'm sorry, I didn't understand your last comment. Could you please?
Sure. If you take what I think you're trying to, what it seems like you're trying to ask is whether this inductive limit works on the compact intervals and then going up. But this doesn't work even just on the level of topological spaces before the graph structure. So if you consider the interval negative n to n, continuous functions on that is a unital C-star algebra, but it doesn't embed into C0 of the real line.
Yep.
Because there is no idempotence in C0 of the real line apart from 0. So you can't send a unit to anything. Yeah.
Yep. Yes, so you might be right.
But yes, but it would be possible that in the context of topological graph, this would be an inductive limit.
I think the same problem should occur, I believe, because if the unit space is, if the vertex space is non-compact, then the graph C-star algebra shouldn't.
Yes.
But if the graph, it comes down to a unital problem.
we are not considering the algebra of continuous functions on a compact interval, because we are using compact interval as projections of certain CS algebra. So I think that the problem is not that because the functor doesn't assign the algebra of continuous functions on an compact interval. I'm considering the same structure of the graph that MARIUSZ defined, but I replace the real line with a compact interval. So I think it's not really obvious that we have issue of the inductive limit. Maybe I'm missing something.
Okay. So for sure, Jonathan is right that there will be a problem, because if you want to have a direct limit, I think already at the level of the vertex space, you also have to have a direct limit, right? And we don't have it here. So the real line cannot be, the functions vanishing at infinity, the real line are not a direct limit of those intervals. It's more of in this, it's either more of in the kind of like an inverse limit or nothing like this, because if you look at all functions on the real line, then of course, but this is not a C-star algebra, it's a pro-C-star algebra, and the pro-C-star algebra is an inverse limit, right? So I don't know.
May I comment on this?
Go ahead.
So my comment is that the problem is that if you consider functions on compact subsets, okay, then you should think about them not as algebras, non-unity algebras. They are ideals. Yes. Okay, and already in the case of topological spaces, local topological spaces, if you have an exhaustion of your space by compacts, okay, then you obtain a system of ideals. They are not algebra homomorphic. Algebra homomorphisms are not enough. You have ideals extended by zero. Okay? So speaking about morphisms between algebras is not proper here. It's not appropriate here. Because it's a question of the system of ideals rather than homomorphisms of non-unitary sister algebras. Yeah. I have a question, if I can. If we consider discrete graphs, then many discrete graphs can have the same sister algebra. And there are known some moves, some operations on graphs leading to the same sister algebra or some sister algebra up to Morita equivalence. In your case, when you have a discrete graph representing the same sister algebra as your topological graph, can you relate these graphs in terms of some operations on graphs, some modifications of graphs?
Yeah, how about topological outsplitting principle?
Yeah, that's a good question. I don't know.
Because your examples suggest that at least some vague shape of these diagrams must be somehow related, but it's very elusive to conjecture what should be this transformation from a discrete graph to discontinuous, or maybe into the opposite direction.
Maybe you can say something about the dynamical behavior, like they are orbit equivalent or something like that.
Maybe.
As you can say, and this you could say at the level of the topological graphs, I guess.
Yeah.
Maybe. Another thing I was wondering is there any criterion for, like, or no, a good recipe for spotting generators of K1 theory? For graphs, for directed graphs, it's like something like loops, okay? So I was wondering, in the cross-product situation, with the easy case that you you showed. Like, could it be like if we take this and try to look for loops there, one could say, okay, try to find periodic points in this z action on the space X, okay? Or like asymptotically periodic stuff. Could this give, not each one, but special asymptotically periodic orbits or periodic points give generators somehow? If you translate them in the Caesar algebraic setting, of course, as elements in the Caesar algebra or over it.
But you can also ask this question about K0. I mean, for discrete graphs, you know that K0 is always generated by vertex projections. So I'm wondering if the same is true here.
Yeah. It's just that I care more about the K1.
Because of the presence of continuous parameters.
Yeah. Not that I don't care about K0, but yeah.
Yeah. So I don't know. I wasn't looking at K theory for now for those. I only know this one result about Katsura where he writes down the 6-term exact sequence, and you can try to look there, right? If there's any way of finding, is it periodic points? I don't know. But for those algebras, this should be just your Pimsner-Wojkulescu, right? 6-term exact sequence.
Yeah, but they don't give generators often.
Okay. So then maybe it's not easy to get the generators from
No,
this.
it's not an easy thing. Yeah.
Yes. So in that sense, I have to. So thank you for this comment, because I'm right now we're trying to finish this paper, and I was looking for some motivation arguments to think about why this approach of decomposing and gluing would be interesting. So maybe somehow we can get some generators of K theory.
Milnor, right?
Yeah. But I don't know for now.
Okay, I think it's time to wind it up. So unless there is some really emergency question, because our discussion is already like 40 minutes long, which of course I enjoyed. For me, it's early in the morning. It's like 10 a.m. So I have no problem continuing. But I suppose Mariusz must be tired. So is there any further necessary question for the time being or comment? Well, if not, let us thank Mariusz again.
Thank you.
Thank you for your very interesting talk.
Let me stop recording, but don't go away.